All right, today we're going to tackle a classic problem that really gets to the heart of the single most important principle of space travel, how rockets actually work. We are going to solve the rocket equation step by step. But first, just think about that for a second, right? Here on Earth, a car pushes against the road, a swimmer pushes against the water. But in the total vacuum of space, what is there to push on? There's nothing. And that is the central puzzle of space travel. And the answer, well, it lies in one of the most elegant and beautiful ideas in all of physics. And here it is. This is the exact problem we're solving, straight out of a classic physics textbook. Our mission is this. We've got a rocket just floating in space, starting from a dead stop. It has an initial mass, which we'll call m0. As it starts firing its engine, it throws mass, fuel, out the back, so its own mass starts to drop. We need to figure out its exact final velocity, v, at the very moment its mass becomes m. Now, before we can jump in and solve our specific problem, we need to kind of build our main tool for the job. We have to derive the general equation that describes any object whose mass is changing over time. You know, the problem itself actually gives us a little hint. It tells us to use a formula from the problem right before this one. So where does that formula come from? Well, it all boils down to one of the most fundamental laws in the entire universe, the conservation of momentum. And here it is, our master tool. This equation can handle any object that's changing mass. So let's break it down real quick. On the left, you see mdv dt. That's just a physicist's fancy way of saying mass times acceleration. You know, good old F equals ma. On the right, that first term, F, stands for any outside forces, like gravity or air resistance. But the real magic, the part we care about, is that last term, u dm dt. That is the thrust. dm dt is just how fast the rocket is losing mass, basically its fuel burn rate. And u is the speed of that exhaust getting shot out the back relative to the rocket. That's the push. Okay, we've got our general purpose tool ready to go. Now, let's start our journey to the solution by applying it to the very specific conditions of our rocket problem. And this is where things get a little easier for us. The problem states the rocket is in the absence of external forces. What does that mean? It means that that F term in our big equation is just zero, gone. We can just erase it. The problem also says the rocket starts from rest, which is going to be important in a minute. So with that one simple little change, our powerful general equation gets a whole lot cleaner. So with no outside forces, we are left with this beautifully simple differential equation. And what it's telling us is actually pretty profound. It's saying the rocket's change in momentum on the left is caused entirely by the momentum of the gas it's shooting out on the right. Every tiny little bit of mass, dm, that gets thrown out gives the rocket a tiny little speed boost, dv. So how do we actually solve this thing? Well, we use a classic math trick called separation of variables. And you can really just think of it like tidying up your desk. We're going to put all the velocity stuff, the dv, on one side, and all the mass stuff, the dm and m, on the other side. This one little step gets the equation all prepped and ready for what comes next. Okay, so what we have now is an equation for one tiny infinitesimal kick in velocity. But we don't want just one tiny kick, right? We want the total final velocity after the engine's been burning for a while. So how do we add up all of those millions and millions of tiny little pushes? We integrate. Integration is really just a powerful way of summing up an infinite number of tiny little pieces. So on the left, we're going to sum up all the velocity changes, starting from our initial velocity, which was 0, all the way up to our final velocity v. And on the right, we'll do the same for the mass, summing up the effects from our starting mass, m0, all the way down to our final mass, m. And when we do that integration, this is what pops out. The integral of all those little dv kicks is just the total velocity, v. And the integral of 1 over m with respect to m gives us the natural log of m, or ln of m. So our raw answer here is the exhaust velocity, u, multiplied by the difference between the natural log of the final mass and the natural log of the initial mass. Yeah, it looks a little messy, but it is correct. But we can clean this up. There's a fundamental property of logarithms that says the difference between two logs is just the log of their ratio. Applying that simple rule cleans up our equation quite a bit, and it gets us just one step away from the final classic form. And just like that, we've arrived. We have solved the problem. And in doing so, we have derived one of the single most important equations in the history of science and technology, named after the visionary who first figured it all out. This is it, the Tsiolkovsky rocket equation. Now you might notice we flipped the fraction inside the log from mo over m to m over m naught. Why do we do that? Well, there's another log property that says ln of a over b is the same as minus ln of b over a. We make this little switch because the initial mass m naught is always bigger than the final mass m, which means the ratio m naught over m is always greater than 1. And that makes the logarithm and our final velocity a positive number, which just feels more natural. So what did we really just do? Sure, we solved a textbook problem, but what we actually did was derive the absolute cornerstone of astronautics. This is the equation that governs the design of every single rocket ever launched. It tells us, flat out, that a rocket's final velocity depends on only two things. One, how fast you can throw stuff out the back, your exhaust velocity u, and two, what fraction of your rocket's starting weight is fuel, that mass ratio, m0 over m. So we have the equation, but what does it really tell us? I mean, deriving it is one thing, but truly understanding its profound implications, that's the real key. Let's break down what this formula reveals about the incredible challenge of space travel. And this table right here perfectly illustrates what's often called the tyranny of the rocket equation. Because of that natural logarithm, your gains are not linear at all. Look at this. To get a final velocity that's equal to your exhaust velocity, you need a mass ratio of about 2.7. That means 63% of your rocket has to be fuel. Okay, but to get twice your exhaust velocity, now you need a mass ratio of 7.4. Suddenly, 86% of your rocket is fuel. And to get 4 times the exhaust velocity, you need a mass ratio of almost 55, which means over 98% of your rocket must be nothing but fuel. This is why rockets are these enormous, fragile structures that are basically just gigantic fuel tanks with a tiny little capsule on top. So when you're solving these kinds of problems, please keep these things in mind. First, the sign conventions for U can really trip you up. Second, always remember it's not linear. Doubling the fuel gives you diminishing returns. Third, the mass ratio is king. That's the number you have to maximize. And finally, never forget that our perfect solution here was for the vacuum of deep space. Down here on Earth, you're fighting gravity and air drag the whole way up, which makes the challenge exponentially harder. And this is the dream that this beautiful piece of physics makes possible. See, Konstantin Tsiolkovsky, the man who first derived this formula way back in the late 1800s, he wasn't just solving a cool mechanics problem. He was laying the mathematical foundation for all of humanity to one day leave the cradle and explore the cosmos. So I'll leave you with this final thought. This equation, it shows us the pathway to the planets, but it also reveals the immense, almost impossible challenge of traveling to the stars. A chemical rocket making that kind of journey would need a mass ratio in the millions. It would have to be bigger than a mountain. So the very equation that opened the door to space also shows us its limits. And the question for the next generation of scientists and engineers is, what comes next?